Stacy, I don't assume you've had a chance to work with a analytical balance or a chemical balance.
No, I haven't.
Well, they're a real challenge because you have to watch almost everything because they're so sensitive. Now, ordinarily, you've seen them with two pans or something on the weight that you move down.
Yeah.
Well, here's the same idea, but this one is electronic in that it dampens out very quickly so it doesn't vibrate back and forth, and you can get the reading right here.
Yeah.
Right now, it needs zeroing. See that bar down there?
Yeah.
We'll push that one bar.
Okay. But it was jumping around. How come?
Well, it's very, very delicate, as I say. Watch, I'm going to wave my hand at the pan up above.
Okay. Oh, it went up to about 0.12. Yeah.
Yeah, just the
air?
The air moving against it can do it. So they very often put it in a glass cabinet so that the air currents can't affect it.
I see.
That's why it's such a challenge to work with one of these, because you have to watch all of those things. So I thought I'd give you a little problem. Here is a piece of paper. Would you tell me how much a piece of paper weighs?
All right.
0 at first. It's stuck at 1 there.
There you go.
Okay, here you are. What does it weigh?
Weighs about 4.53.
That's grams. Okay, now I'd like you to tear off a piece that weighs about half a gram.
Okay, so it weighed about 4, so I'll have to divide it into about 8 sections.
Right. See how close you can.
0.48, 49.
49, 48,
So that's
49.
pretty close.
Very close indeed, yes. That was a good guess. Now, to give you an idea how sensitive the balance is, I want to put that piece of paper down over there. We'll refer to that later. Here's a match and a battery clip. How much does it weigh?
About 7.54.
Okay. I'm going to have you light the match.
Okay.
What do you think will happen to it?
Well, it's going to start burning, and the sulfur and the wood are going to start going into gases. So it should weigh less.
Okay, here's a match. Light that match.
All right.
Here, I'll take this one now. And I'll blow on it away from the scale.
Yeah. It's already dropped about 3. Now it's dropped to 4.04 grams. 5, 8, 9, 10. It's already dropped 0.1 of a gram.
Yeah. So you guessed correctly in that some of the chemicals in the match are being changed into a gas and are being given off into the air, so it should weigh less.
Uh-huh.
All right.
Lost about 0.2,
Yeah.
0.19 of a gram.
Okay, now I have a sort of nice little challenging puzzle for you. Here is a flask.
Okay.
Here's a stopper that goes in the flask. And here is a headache tablet. I'm going to put this off to the side like this, and I want you now to get as close as you can to having that whole group. By adding water, the whole thing is going to be about 300 grams. So go ahead, start.
It's at about 148 now. So I have about 150 to go. 170, 180.
Stop just short, and then you can use this medicine dropper to get closer.
Okay. 250, 60, 70, 95.
Okay, now the medicine dropper. And notice, as you drop it in, how much a drop weighs.
Okay, I'll drop one drop and we'll see. It's 37 now, so that one weighed about 11.
Yeah.
Not 11, pardon me. About point. Yeah.
Keep going. You got a whole 5/10 of a gram, half a gram to get up to 300.
We're really close.
Okay, careful. Oh, 49, 50, 60,
70, 80, 90.
Close enough.
97?
7, that's close.
One more drop?
All right, one more drop. I think you'll go over probably.
Yeah, I went
yes,
over
you
by
did.
about 6.
Okay. Now, the reason why I wanted you to do all that is because you've weighed everything now, right?
Yeah.
Okay, now I'm going to put the headache tablet inside the flask on a string. I'll pull it off here for a minute so I can put this in tight, but not too tight. When I put it back on, should weigh the 307.
Yeah.
Okay, now pick up the flask and move it around a little bit so that you get water on the headache tablet.
Okay.
Until it drops off into the water.
All right.
Okay? There you go. Still should weigh the same?
Yeah, it's weighing the same.
Okay. Now, what should happen, however, because why does it weigh the same when here, see all that chemical reaction going on in there?
Because all the gas is being trapped
Yes,
by
but
the
watch what's
stopper.
happening to that stopper.
Is it going to pop off?
Well, I don't know. It depends on how much pressure we can get in there. I can shake it a bit, perhaps. There, it's popped off.
Oh,
Wow, it hit you right on the
Yeah.
head, too. Some of the gas is still being given off, right? Mm-hmm. But let's not wait for it to finish. I'll put the stopper back on. How much gas did you give off?
About 0.5.
Yeah, something like that,
Mhm.
right? Remember how I had you weigh this piece of paper?
Yeah,
And what was that?
0.5.
0.5? So now when somebody drops a headache tablet into water, can you tell them how much gas is given off?
0.5.
Yeah,
Half a gram.
because you were able to use a very delicate balance. Jason, have you ever had a pop gun when you were a little kid? Put
Yeah,
a
I
cork in
did,
the end
yeah.
with a little string, then what happens?
Well, I'd pump it up,
Pump it
and
up?
I'd pull the trigger and pop.
Out would go, I think. Well, you can make one of those. That's a lot of fun. All you need is a metal tube like this or a plastic one. The important thing is that you get a piece of wood that just slips inside like that. Okay, now what we have to do is capture the air. And here's how we'll do that.
Oh, like this is like the cork.
Right,
I
that's
get
going to be
it.
the cork. But it'll work, as a matter of fact, as two things. Here's the cork, but now you had a plunger. I think you now understand the idea.
Yeah, so I get another one.
All right. Okay, now when you start with the plunger, here, just hold it here like this.
Okay.
What's going to happen? Oh, you've already compressed the air. It's coming out a little bit. Okay, what will happen now when you push with the
It'll
plunger
pop
like
the
that?
end out.
Why?
Well, because the air inside is getting really compressed, and it's going to push the other end out because
Yes.
there's not enough room for it.
In other
the
words,
air.
the pressure will get greater and greater and greater as the plunger goes here until the pressure is stronger than the friction holding the plug in.
And out it'll come.
Okay, so try. Do the firing it that way.
Okay.
Okay, not too hard. Look what. Makes a nice
Wow.
popping sound too.
Yeah,
doesn't
that's
it?
neat.
Now this principle of the pop gun like this is also used in regular commercial and professional guns. You've seen guns in which you pump them up like an air rifle.
Yeah.
It suddenly releases the pressure and out goes the bullet. Others use containers of carbon dioxide gas and fire.
Oh, yeah.
Same idea.
Like those little cars that you put a CO2 cartridge
Right,
in and
out
shoots
comes the
them off.
gas. Okay. So here, take your ammunition and your pop gun and stand over there, and I'll set up a target for you.
Okay. Okay.
Not exactly the most accurate gun in the world, but let's see how you do. Go ahead, fire. Ha, a little low. Try again.
Okay.
Now, the plunger now becomes your ammunition, right?
Yeah. There.
Boy, you pushed them both out. Anyway, you get the general idea. You can make these for your young friends because they have a lot of fun firing the thing, and then they really can't hurt anybody. Some people think of a zebra as a horse with stripes, but that's not quite accurate. It's true that, like wild horses, they tend to live on grassy plains in herds and prefer to graze during the early morning and evening hours. They're sociable, often grooming each other with their teeth to get rid of the insects that live in their hair. They also roll in the dust when it's handy, or scratch themselves on a convenient tree. While it's true they are members of the horse family, there are many differences. Think of what a typical horse looks like as you look closely at a zebra. Is it fatter or leaner than a horse? The zebra is much more rounded. How about the size of its head compared to the rest of its body? For the size of its body, the zebra's head is larger than a horse's. Is its mane longer or shorter than that of a horse? It's much shorter than the manes of most types of horses. Finally, does its tail look like that of a horse? Hardly. A horse's tail is made up of many loose strands, while a zebra's has a tuft of loose hair only at the tip. But the most distinguishing characteristic of a zebra is its stripes. In fact, you may wonder if such distinctive markings would make a zebra easy to see by their chief enemy, the lion. The stripes tend to break up the outline of their bodies, making them much more difficult for a lion to see. You could identify a specific individual from the pattern of its stripes because it's unique on each animal, in much the same way as your fingerprints are unique to you. So you can think of these easily recognized animals as horses with stripes, but remember, they're not horses at all, but a unique species known as zebras. Karen, here's a tricky little problem for you. Here's a glass of water, a cork, and a nut. I'd like you to tell me, when you put them inside the glass, which will sink and which will float.
Well, I think the cork will float because it's fairly light, and I think the nut will sink because it's fairly heavy.
Okay, go ahead, try it.
Sank like a rock.
All right. Okay, very difficult, right?
Yeah.
Now, however, why does one float and the other sink?
I don't know.
Well, think about it this way. If you had a piece of water that was exactly the same size as this cork, and you weighed them both, the water would weigh more than the cork.
Oh, okay.
Therefore, the cork will float.
I see.
Okay. What if you had a piece of water exactly the same size as the nut, and you weighed the two of them? Which would be?
The nut would be heavier.
Right. So that's why it sinks.
Yeah.
Okay. So whether something floats or not depends on the density of the object as well as the liquid. Okay. Keep that in mind now, because here is a glass that has 4 different liquids in it.
Oh, neat.
One on top of the other, and here's what they are. Now, these are relatively common liquids. The mercury you find around the house in a thermometer, right?
Yeah.
The second one is a trichloroethane, is a sort of cleaning fluid. Then water, and finally mineral spirits. That's the sort of stuff you take paint off with and use, okay?
Yeah.
What can you tell me about their densities?
Well, mercury is really dense, and then trichloroethane is the next dense, and then water, and then mineral spirits is the lightest.
And they don't mix either, by the way. They're not miscible.
Yeah.
Now, what I'm going to have you do is to drop these objects in, just like you did the cork and the nut before.
Okay.
But I have duplicates of them with little pieces of tape on them like this. And I would like you now to stick them on the chart where you think they're going to float.
Okay. I think the cork will float on the mineral spirits,
Okay.
and the marble will float on the trichloroethane.
That's plastic, by the way, and not glass.
Okay. I think that the
Candle.
candle will float on the water, and that the
Nut will
go on the mercury.
Okay, now all you have to do is try it. Which one are you going to put in first?
I'll put in the nut.
Okay. Clunk. Where did it end up?
Right on top of the mercury.
Okay, next.
Then the plastic marble. Right on top of the trichloroethane.
Right. The cork.
then
Or you're going to put the candle
put
in
the
next?
candle in.
Okay.
The candle right on top of the water.
But on the bottom of the mineral spirits. So where should the cork end up?
On the top of the mineral spirits.
Right. Hey, very good.
Neat.
That's called a density float, and you were absolutely right. So what is the principle? When will something float or sink?
Well, the object will float when it's less dense than the liquid that it's supposed to be floating in, and it'll sink when it's more dense than the liquid that it's supposed to be sinking in.
Very good. Here's a very popular and quite simple optical illusion that you might be able to do yourself. There is a cake with a piece missing, right?
Oh, yeah, okay.
Okay. All you have to do is find the missing piece.
Well, I can't see it there.
Well, watch. I'll show it to you. All I have to do is turn this upside down like that.
Oh, there it is.
And there it is.
Oh, wow. Like in a
Okay.
sort of a plate or something.
Right. Like, now you can see almost an empty plate with one piece of cake, right?
Yeah.
Well, if you turn it the other way, you see a full cake with one piece missing. Now, the big question is why? Why does that optical illusion work?
Well,
You got any ideas?
I think maybe it's just that when you look at it this way, you can see that
the way they drew it, it looks in. When you turn it around, it looks out.
Well,
just the way they drew
now
it.
think of it this way also. When you ordinarily look at a cake or a pie sitting on a table,
Yeah.
you see it from this perspective, don't you? You look
Yeah.
sort of down on it. So when I show you this, you immediately think of it as looking down on it, so that piece looks like it's missing. Now when I turn it upside down, you still sort of look down on it, don't you?
Yeah.
So now you see where the missing piece is. If you try real hard, see if you can find the missing piece now without turning it upside down. Take a look at it. Imagine that you're on the floor looking up through a transparent table and transparent dish.
I'm looking up.
Up?
Okay.
Right. When you see it from that perspective, I think you might be able to see the missing piece.
Oh, there, I see it.
You see
like
it?
this is the bottom right here. Oh, I see it
Yeah,
now.
okay. Yeah, you're looking at now if you turn it over the other way, can you see the whole cake? Again, looking up underneath from underneath a transparent table and a transparent dish.
Oh, that. Yeah, I see it now.
You say it now?
Yeah.
Okay. Well, it's a very simple optical illusion that you can try. All you have to do is draw an ellipse and put a piece of cake in there like that, and you can fool your friends.
Yep.
Have them find the missing piece of cake. You no doubt have twiddled your thumbs like this. What if you did the same thing with these two identical threaded rods? Hold them so they can't rotate and keep their grooves intermeshed. Will the ends move apart, come closer, or stay the same distance from each other? Remember, the rods won't actually turn, but simply go around touching each other in their grooves. Well, you can see for yourself what happens. While one thread is in effect going to the right, the other is going to the left, so the ends stay right where they were. Scott, I don't assume you've ever had much chance to experiment with fireworks.
No, I haven't.
Yeah, it's pretty dangerous stuff.
Yeah.
You've seen them, though, I assume.
Yeah, at a circus and stuff like that.
Yeah. Well, today you and I are going to investigate some of the aspects of fireworks, and we have to be very careful. I have a fire extinguisher in the back standing by,
Okay.
made very small amounts of each material. And the first thing we're going to do is just burn some of the chemicals. Do you know what canned heat is?
Stuff like oil and stuff like that.
Well, it's actually a material that's sort of solid alcohol that they put in the bottom of chafing dishes. You know, and you see it, the little flames underneath, that keeps food hot. Well, I have some in
Okay.
each one of those little holes in the cupcake liner. And then I added various chemicals. So now I will light the first one. That's just, this one right here is just plain canned heat. And you'll see the kind of flame we get from that. Now we can see them better if I turn out the lights. You put on your safety
Okay.
glasses. Good idea.
Oh, it's just kind of blue and
Yeah, sort of a
bit
slight
of
bluish
orange
effect.
on the top, yeah.
Okay, now I'll light the one next to it, and you'll see what effect a chemical can have.
Oh, it's green.
Yes,
Neat.
that's the
That's
green.
pretty color.
So if you're going to make fireworks, you put some of that chemical in there to get that color. Okay, here comes that one.
Oh, it's kind of a bluish green to
Yeah,
it.
weak bluish green.
Yeah.
Okay,
That one's just kind of
yellow.
yellow. Yeah.
That
That's
one's
an
more
orange.
yellow.
Yeah, an orangish yellow.
Okay, here comes the last one.
Oh, it's red,
Yeah,
kind
it's
of.
nice and red.
That's
So you
pretty.
see, the fireworks manufacturers can put the various chemicals together to get the sort of explosion they want. Then they can put in these various chemicals to get the colors that they want.
Oh, yeah.
Okay? Now let's put it out. How come that puts it out?
Because it burns up all the oxygen.
Let me turn the lights back on. It burns up all the oxygen?
Yeah.
Well, this just keeps the oxygen from getting there.
Yeah.
Okay. Well, now you get the general idea that you can put various chemicals into a combination of things that have usually some carbon, which is what they usually burn,
Yeah.
and then some oxidizer of some kind, and finally ignite it, and then you get the colors. I don't know if you and I have ever played with flash paper, have we?
No.
Well, here's the tongs. Put on your safety glasses again. I'll light the candle, and this is a kind of paper that has been treated with sulfuric acid and nitric acid so that there's no flash left behind, no ash left behind,
Oh, yeah.
but definitely a flash. I'll light the candle, and you hold the paper over the candle. Sort of, do you want to get it out of the way here, and I light this? Okay.
Okay.
Okay, now bring the paper down slowly over the top of the candle flame. And this is what plain flash paper without any chemicals in it is like.
Whoa.
Nice yellow flame, right?
Yeah, that's
and notice it
neat.
completely disappeared?
Yep.
Okay, well now I soaked some of the chemicals that you and I just put in that dish. I soaked the pieces of flash paper in it. And you should now get a different color. Here, this one is copper chlorate.
Okay.
Hold it over the top and see what you get.
Oh, it's blue.
Nice blue
Whoa.
color, right. You see why I'm careful about all this? Because
Yeah.
you have lots of fire.
Yeah.
Finally, one of my favorites, the strontium.
Strontium chloride.
Try the strontium.
Okay. Here it goes. Oh, it's red.
Nice
oh,
and red, yes.
That's neat.
Okay, so now, you want to blow the candle out, please? Okay. Now you see how you can get various colors in the fireworks, but sometimes they have a nice big flare that just is nice and brilliant and bright.
Yeah.
Okay, they use a different system for that. In fact, they burn a metal. And here I have some over here. Aluminum. You wouldn't think aluminum would be much of a fire producer, would you?
No.
But there's powdered aluminum, which I'll put in here like this. Now what we need to do is give it a supply of oxygen. And here's one of my favorite chemicals that has a supply of oxygen in it. I'll mix them up just a little bit. Now I'd like you sort of to stand back,
Okay.
because I'm going to put a drop of water in there, and the drop of water will hopefully set off the chemical reaction, and you'll see what they use this combination for in fireworks.
Oh. Oh, neat.
You know the big flares that go up?
Yeah.
They really, you know, sometimes fall down with all kinds of streamers.
Yeah.
Well, they very often put a combination involving aluminum powder. Now, I would not suggest that you do any of these at home, because obviously it's pretty dangerous. And I want to get all of this out of the way because I'll show you some of the fireworks that you and I are going to set off.
Good. Oh, those
How do you
are
like
big
that?
ones. Those are big.
In fact, here's another one, a cone shape. And I have no
neat.
idea what they're going to do. This one's called Cave of Pearls. So
That's a neat name.
that sounds like a good Wizard
Wizard
Mine.
Mine.
Oh, that sounds like a great one. Floral Fountain. So I expect that's
Neat.
going to have some of that stuff in it. Anyway, we'll fire these later. But I broke apart one of them so we could take a look at what's inside. And I would not suggest that you do this either, because there's what's inside of one. When I started, it was one about like that.
Oh, yeah.
Then it had a plug like this at the end. And then, see the combinations, that carbon that I told you about?
Yeah.
Carbon is usually one of the things that's present because that combines easily with oxygen. And obviously there's an oxidizer in there, and then some of the chemicals, and by putting it in the tube in a certain way, they can get it to fire out and flare and so forth. All right, so are you ready?
Yep.
Meet me at the parking lot at the school just about sundown.
Okay.
I have special permission from the fire department to be able to set these off, so you should see a real fireworks display.
Okay.
Okay, meet you then. Okay, Scott, here's the first one, big firecracker-looking thing, right?
Yep.
Okay, I've got my glowing punk ready, so I want you to go back and stand there by the fire extinguisher.
Okay.
Safely out of the way, and I'll start it, and let's see what happens.
Oh, totally bogus, man. Oh, that looks so cool.